Hello everybody, this is Dr. Dave with Physics 152. I wanted to give you a quick introduction to magnetic fields. This is one of those topics that I think is really helpful if you do open up your textbook and take a look at the images there. They're going to have much better renditions than I'm able to draw with my limited artistic skills. Here's the main takeaway. Static or non-moving electric charges produce electric fields. And now we have magnetic fields, which turn out to be related to electric charges. However, they come about from moving charges. And we're going to start out by examining the magnetic fields produced by currents. However, you don't need a large number of charges moving, you just need one. Right now we're going to look at currents in total. So what we have here is this was a wire, this black line is a wire. We have a current denoted by this green arrow flowing to the right. First thing we need to do is introduce the right-hand rule, and what this means is you're going to take your right thumb and point it in the direction of the current, and then your fingers are going to be the direction of the magnetic field. So here, if you point your thumb to the right, your fingers should be pointing out towards your face, and if that's doing so, that's this right here, and the field then, if you were to curl your fingers around, go all the way around in a circle, all the way back. And your textbook just has much better pictures of this than I possibly can. I do need to point out that these are what's known as magnetic field lines and not magnetic field vectors. They are related, but they are not the same thing. These are always closed loops. I'm just trying to show partial depictions here. If you were to put yourself over here and look straight down this wire, kind of giving yourself a side view, you would see the current flowing out of the wire towards you. Again, we're going to use the same convention we did in Physics 150. That is, this symbol means out of the page, and this symbol means into the page. So now in this depiction, we've got the current of the wire flowing out. If you put your thumb pointing up off your paper out of the page, you'll see that your fingers are curling in a counterclockwise circle as shown. This is again known as the right-hand rule. This allows you to determine the direction of the magnetic field lines, which are shown in blue. The magnetic field vectors, which we're going to be primarily interested in, are shown by these red vectors here. Now here's how to understand how to use the magnetic field lines to construct the magnetic field vectors, and that is the magnetic field vectors will always be tangent to the field lines. So at any point along here, if you were to draw a tangent direction, you would get the direction of the field vectors. And they don't curl like this. They are straight vectors. And again, they're representing the field at that point. They're not representing the field here, 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 and here. They're representing the field at that point specifically. So they're always pointing tangent to the field line circles. And so that means that they're not always pointing left, down, up, or right. They're pointing whatever that tangential direction is. So if I have a current here, and I'm looking at the field here, now I'm pointing down like that. What you can do to help yourself figure out which way those fields should be pointing is you can draw a radial line from your current to where you want to know the field, and that's always going to be perpendicular. So as you see here, this is always going to be perpendicular to that spot there. Okay. All right, so let's ask what we're going to do with this. We're going to look at fields that are produced by wires, so that if I tell you a current's flowing like this, it's going to produce some field around it, just like an electric charge did. And we're going to look at that dependence just a little bit more. So this is going to be a little bit different than a point charge was. The dependence is going to be based off the distance, not the distance squared. However, we'll see that distance squared will play a role later on. Right now for a wire, it's going to have just a distance dependence, which is the same kind of dependence that a line of charge did have before. So let's look again at our wire, and this time the field is coming out of the page. If we look at some distance d away from the wire, we can use our right-hand rule, again, thumb coming out of the page, and your fingers are curling up around like this. So we draw our sort of radial line out, we draw perpendicular to that to sort of think about the circle moving around, and there we draw our magnetic field. Now again, that first magnetic field vector you draw is arbitrary. You can make it short or long. Please don't make it microscopically small. We want to be able to see what you've drawn. So pick a couple of squares, a couple of boxes so we know sort of what you're drawing, unless you're specified how many boxes to make it. So there I'm going to draw B1, and now I'm curious is how does the magnetic field look at this spot here? Well, as we've learned already in this course, building ratios is super helpful. The more ratios we have, the better life is for us. And so now at this spot here, we say, well, how long should B2 be? Well, we're going to take a ratio of B2 to B1. Now remember, the ratio only cares about differences. So because it's the same current producing it, because this is our new constant called permittivity of free space, is the same because those two pi's are the same. The only thing that matters in that ratio is really the distances. Now I didn't really need the d here since that's the same for each of them, but I put it in just so you could see what's going on. B2 is not d away. B2 is square root of d away. So that means the distance that we're dividing for is 1 by root 2. And the distance here is just 1 by d. And so that ratio gives us 1 over square root of 2, which you may or may not remember from your high school trigonometry courses being 0.71 or 0.71% is sort of how we're going to think about it. So that is if I were to take the length of this vector here and take 71% of it, so maybe about there, that's going to be the length of B2, about 71%. And so we expect that whenever you're drawing magnetic fields, you're drawing these ratios correctly and properly to scale. We expect to see your ratios drawn as appropriate. So let's say you have multiple wires, each of them producing their own magnetic fields. And what do? Well, it's the same thing with electric fields, a superposition. So let's imagine that I had two vectors, vector A and B. I'm going to add them up. Presumably these two vectors are created by different wires. How do I add them up? I take this vector and I put it at the end of that vector and I draw their connection as shown. You could also have taken this vector B and put it at the end of vector A. So you would have had vector A and vector B and gotten the same A plus B. So this is just vector superposition in the same way that we've had vectors before. All right, so that's magnetic fields due to currents. Now what about forces in magnetic fields? Well, what we're going to look at right now is forces that charges feel, and later we're going to get into forces that wires feel. But just to contrast this to the electric field as we just did with the other stuff, electric field, your force is always just QE, which had a really interesting character. That is, it said the force is always going to be parallel or anti-parallel. Anti-parallel is just a fancy way of saying in the opposite direction. It's always going to be parallel or in the opposite direction of the electric field, right? So if your electric field pointed this way, your electric force would either be this way, or if it was a negative charge, your force would be that way. But things are a bit different, a little bit more complicated now in the magnetic field case. In this case, because this weird new operation, which we call a cross product, which we did see with torque just a little bit at the end of Physics 150, the force is always going to be perpendicular to the velocity and to the magnetic field. So what does that mean? Well, if I have velocity this way and a magnetic field this way, then my force has to be perpendicular to both of those. So the only possible way I can do that is to either have a vector coming out of the page or a vector going into the page. Again, I have to be perpendicular to both of them simultaneously. So here we're going to get our second form of the right-hand rule. Our first form of the right-hand rule was understanding the direction of the magnetic field in response to a current. In this form of the right-hand rule, we're going to use this to understand the cross product, which the other one is too, but that's a little bit more complicated. So what we're going to do here is we're going to point your fingers, your four fingers, in the direction of V. So if you do that, you put your four fingers in the direction of V, it's kind of pointing away from your body, and then you're going to turn your fingers towards B. So if you do that, your thumb should be pointing straight down into the page. And so what we say is the direction of V cross B is into the page. So again, just to do that, we put your four fingers in the direction of V, and you turn your fingers towards the B vector, right? So your hand's pointing this way, and then you curl your hand towards B, and that makes your thumb pointing straight down. So what we then say is V cross B is into the page, and then this Q plays the same role that it did in electric fields. That is, if it's a positive, it's in that same direction. If it's a negative, it's in the opposite. So what we then say here is if it's a positive charge, the force is into the page. If it's a negative charge, the force is going to be the opposite of that or out of the page. Let's do another example. So here we're now going to say V is up the page and B is to that side. So now I'm putting my hands straight along the direction of V. I turn my fingers towards B. And as I do that, what am I going to see? My thumb is pointing straight up out of the page. So if it's a positive charge, the force is going to be straight up out of the page. And if it's a negative charge, the force is going to be into the page. You simply have to know how to do this. Right now we have two right-hand rules. The first right-hand rule that we're going to use is direction of magnetic field due to current. The second right-hand rule that we're going to use is going to be the direction of V cross B. And that will lead us directly to the force. And we're going to have multiple forms of the right-hand rule. We're going to keep introducing them. All the principles will be the same. You should be able to keep them straight. If you're ever confused as to which form of the right-hand rule you're supposed to use, please ask your TA, classmates, or instructor. So this tells us very quickly how to find the direction of V cross B. But now we want to know how long is it? How big is that force? Well, this is going to have the following form. We say that the magnitude of the force, again, we're not writing with a vector symbol. What we're really saying is there's the vector, I'm taking the length of that vector, and that's what we mean by F. So the length of that force is the magnitude of the charge. There's no plus or minus here, just the magnitude of the charge, the magnitude of the velocity, again, no plus or minus, and then B. And now sine theta is where you're going to get all of your kind of action from. So of course you remember that when two vectors are pointing in the same direction, the angle between them, that's what this theta is talking about, the angle between them is going to be 0, and then of course sine of 0 is 0. So what we see here is that their force is going to be 0. That is, we're never going to develop a force when the magnetic field and the velocity are in the same direction. Similarly, if the velocity is this way and the B field is that way, what are we going to find out? We're going to see that theta is 180, and of course we all remember that sine of 180 is equal to 0, so therefore the length of the force will be 0, therefore there will be no force produced. There's a lot going on in this chapter. Magnetic fields can seem complicated, but if you work them out very carefully, hopefully you will see that they're really not much more difficult than electric fields were. We just have to know what we mean when we say the words. So when we say magnetic field lines, we're talking about things that are not vectors. When we're talking about magnetic field vectors, right, we're explicitly drawing vectors. Whenever we have vectors from multiple sources at the same location, we're going to superimpose them, just like we did with electric fields. When we find the force, it's going to be just a little bit more complicated than it was with electric fields, but not too bad. We're going to simply find this new thing with the cross product, which will seem a little awkward at first. If you ever find your hand bending in an awkward way, just turn your arm around, and it should be a little bit easier to work with. Please do ask us if you have questions. Thank you.